Right, so this is option D of IB chemistry. Now this is a quick overview of the lesson, right? And so first things first, we're going to start right here. So we have drugs and medicines. Well, drugs and medicines are used interchangeably. Perhaps there isn't much of a significant difference between them, but it's best to know that medicines are mostly used for medications and are aimed at restoring mental or physical stability to a person, while drugs refer to any kind of substance used to gain control over your body or your mind. Now we have different types of methods of administration. We have 6 types, right? We have intravenous, intramuscular, oral, inhalation, subcutaneous, and rectal route. So intravenous, from its name, it's pretty obvious. It's into your veins, like it's injection into your veins. Intramuscular is injection into your muscle, perhaps your buttocks muscle. And then oral is of course through your mouth. And then inhalation is through your lungs, like you inhale it in, right? And then you have subcutaneous, which is through the skin, if I'm not mistaken. Then we have the rectal route, which is just up your butt. All right, I'm kidding. It's upper rectum. Now, right. Now let's define bioavailability. So bioavailability is a fraction of the administered drug that enters the bloodstream. And the factors that affect bioavailability are, firstly, method of administration. So if the drug or the medicine is administered through intravenous, well, it has higher bioavailability, right? Because it's right into your veins. It instantly enters your blood flow, and so that's 100% bioavailability. Now, if it's oral dosage, well, if you're taking a medicine orally, you should at least take 4 times the dosage that you would take intravenously, right? 4 times the dosage of an intravenous administration. And then what do we have? We have, other than methods of administration, we have the solubility and polarity of the drug, which affects the bioavailability of the drug or medicine. So if the drug or medicine is polar, it will be partially absorbed as it cannot cross the cell membrane. So if you remember from biology class in PYP, right, we have lipids. I'm honestly not a biology student, so I don't know. I wouldn't know, but I remember we had the part of the cell membrane, the middle part, where it was, I believe, non-polar. Yeah, so it was hydrophobic. And so if your drug or medicine is polar, it will be partially absorbed as it cannot cross that cell membrane and enter the cell. Now, we also have non-polar, so if it's non-polar, again, it's partially absorbed as well, as it does not dissolve in the body's aqueous solutions or fluids. But what's the solution? How can we solve this? Well, the only solution is you use a drug or medicine that is highly non-polar, right? So that it can cross the cell membrane, but also a bit soluble in aqueous solutions as well. Then the third factor affecting bioavailability is functional groups. So non-polar functional groups enhance the solubility of the drug as it can cross the cell membrane, and so that increases the bioavailability. Now, what do I mean by non-polar functional groups? Well, phenyl groups and hydrocarbon chains are all non-polar, which contribute to the solubility of that drug or medicine. Alright, so that was for bioavailability. And now let's see, what else should I mention? Okay, let's now talk about therapeutic index. So therapeutic index is the ratio between the dosage of a drug that causes toxicity or it is lethal, and the dosage that causes a therapeutic effect. So therapeutic effect, perhaps I should look this up, but in essence it means that it's useful for let me just quickly look. I don't recall. Okay, I don't know honestly. So over here, where the therapeutic window is the range of dosage between the minimum amounts of drug that produce the desired effect and a medically unacceptable adverse effect. And so you'll calculate the therapeutic window or the therapeutic index through this formula right here. So that's the lethal dosage over the effective dosage. Now, the lethal dosage is a dosage that is lethal to 50% of the population. Now, if they'll most probably during their preclinical trials tested on animals, so it's the dosage that is lethal to 50% of the animal population. Now, the ED50 is the dosage that is effective to 50% of the animal population. And so higher therapeutic index or therapeutic window means that a higher lethal dosage is required, right? So if we say that the therapeutic index is higher, it means that the lethal dosage is high, and so a larger therapeutic index is safer and is better, right? Because it means you require more dosage for that medicine or drug to be lethal. But a low TI is means that lower dosage is required for it to be lethal, and so it is harmful. Alright, so that's that, and what else should I cover? Alright, now let's talk about aspirin. So aspirin, right, is something really interesting. I think you would really like it. Right, so aspirin is a type of painkiller, right, and a fever depressant. And so it is formed by, if I can adjust this, right, it is formed by reacting salicylic acid and ethanoic aldehyde. That forms aspirin and ethanoic acid. And so this is called the aspirin synthetic, or maybe synthesis of aspirin, right? And this reaction occurs during the presence of a catalyst known as H2SO4, right? And if you want to obtain pure aspirin, right, because this now has aspirin, there's aspirin and ethanoic acid. So what you do is you gently heat that your product of this reaction, right, to obtain the pure aspirin. That was synthesis. Now just I've mentioned some points about aspirin here as well. So aspirin is largely nonpolar and has low solubility in water. And solubility of aspirin can be increased by reacting with NaOH. Right, so reacting aspirin with NaOH forms an ionic salt. And ionic salt is more soluble in water. So it increases the solubility of the aspirin in water, but not necessarily its bioavailability. Right, so its bioavailability remains the same, because when aspirin reaches the acidic environment of the stomach, it changes back. So what I mean is, so let's say we react aspirin with NaOH, right? And then you give a human being or an animal, whatever, that ionic salt containing aspirin and NaOH, right? And so when that ionic salt that was formed with aspirin enters the enters your stomach, as it is highly acidic, that aspirin, that ionic salt, right, changes back to its unionized form of aspirin. And so that way your body can use that. And so purity, and this is extra information, so purity of aspirin can also be determined by using IR spectra. So I think that is it for the first part. Now, of course, I'm going to have to erase all of this, unfortunately, and then prepare the second notes for the second part of this chapter, whatever you want to call it. Peace.